Alright, so this is our AP Chemistry Chapter 19 lesson video part 1, and in this video I'm going to cover section 19.1 through 19.3. So we are going to jump into chemical thermodynamics. So this is going to relate to our thermochemistry chapter, so you're going to see some stuff that we're going to repeat, and you're going to see some new stuff too. So spontaneous processes. So one thing I do want to point out is now on the AP exam, instead of referring to processes as spontaneous or non-spontaneous, they like to refer to them as thermodynamically favorable or thermodynamically unfavorable. Sorry. So just keep that in mind. So the textbook still uses spontaneous and non-spontaneous, but we'll need to switch that wording when we answer like a free response question or something. So section 19.1 is on spontaneous or thermodynamically favorable processes. So the rates of chemical reactions are controlled by the activation energy. Gosh, sorry, I've been teaching all day today, so my throat is sore by this point. So anyway, the rates of chemical reactions are controlled by activation energy. So remember, the higher that activation energy hump, the slower the reaction. And we can do things like add a catalyst to lower activation energy or increase the temperature so more particles can collide with enough energy to overcome the activation energy hump. But that's what controls the rate of a chemical reaction. Equilibrium, of course, as we've been discussing for 3 straight chapters, is when opposite processes occur at the same rate, so equilibrium is also controlled by energy. So first law of thermodynamics. So there's 3 laws of thermodynamics. We'll get to all 3 of them, but we'll start with the first one. The first law of thermodynamics states that energy is conserved. So of course, energy of conservation means that energy cannot be created or destroyed. Now it can change forms, but the total energy must remain constant. So energy can be transferred to other objects or change form, but total energy of the universe remains constant. And so our formula is delta E, which is your change in energy, equals Q plus W. That means heat plus work. So here's an example of like a pendulum swinging. And you can see as it's swinging, your kinetic and potential energy are both kind of seesawing back and forth, but at all times, those 2 amounts must remain equal. So a spontaneous process is one that proceeds on its own without any outside assistance. Now keep in mind, y'all, a spontaneous process does not necessarily mean fast. It just means it will occur without assistance. The AP exam will sometimes refer to spontaneous as thermodynamically favored and non-spontaneous as thermodynamically unfavored. So just be aware of this. So for example, for the ball to roll down the hill, that's spontaneous. That will just happen on its own due to gravity. But if you want the ball to roll back up the hill, that's non-spontaneous or thermodynamically unfavorable, and you have to apply work in order to get that ball back up the hill. So processes that are spontaneous or thermodynamically favorable in one direction are non-spontaneous or thermodynamically unfavorable in the opposite direction. Okay, so if going to the left is spontaneous, going to the right is non-spontaneous. Wow, I just totally said opposites for y'all, sorry. If going to the right is spontaneous, going to the left is non-spontaneous. Sorry, it's different for me when I'm facing you. Alright, so even though a process is spontaneous, that does not mean that it happens quickly. Okay, some spontaneous processes happen incredibly slowly, but they're still spontaneous. So for example here, iron reacting with oxygen and water to form rust is a spontaneous process, but it doesn't spontaneously turn back into iron. Okay, so that's a non-spontaneous or thermodynamically unfavorable process. So let's look at our first sample exercise together. So it says predict whether the following processes are spontaneous as described, spontaneous in the reverse direction, or in equilibrium. So it says when a piece of metal is heated to 150 degrees Celsius and is added to water at 40 degrees Celsius, the water gets hotter. So yeah, if I drop the hot piece of metal in the water, is the water spontaneously going to get hotter, or do I need to do something to make the water hotter? It's going to spontaneously get hotter. So on the AP exam, of course, we would say it's thermodynamically favorable. Water decomposes at room temperature into hydrogen gas and oxygen gas. Well, yeah, if this was a spontaneous process, then this would constantly happen if you had a glass of water out, and you would see bubbles just coming out slowly or quickly depending on how fast the reaction occurs. We don't see that. So that means this is a non-spontaneous process. So that means it would be spontaneous in the opposite direction. So what that means is in the air, when hydrogen and oxygen accidentally bump into each other, they will spontaneously form water. So this would be spontaneous for the reverse process. All right, and then part C says benzene, which is C6H6. Hopefully you remember that from back when we did Lewis dot structure. It's a ring, hexagon. At a pressure of 1 atm condenses to a liquid at the normal boiling point of benzene. So yeah, if it's at the boiling point, remember, at the boiling point or at the freezing point, you have two phases that exist in equilibrium. Remember when we talked about the phase diagram? So if we are at the boiling point, we have some liquid and some gas in equilibrium. So this would be equilibrium. All right, so y'all tried this one. I'll assume you've done that. We'll look at it together. So it says under 1 atm pressure, carbon dioxide solid sublimes at negative 78 degrees Celsius. Is the transformation of carbon dioxide solid to carbon dioxide gas a spontaneous process at negative 100 degrees Celsius and 1 atm pressure? Okay, so y'all, it sublimes at negative 78. That means it naturally goes from a solid to a gas at negative 78. Well, we're putting it at negative 100, so it hasn't reached its sublimation point yet. So it would not be spontaneous to go from solid to gas. In this case, the opposite would be spontaneous, to go from gas to solid, because it's too cold. It hasn't reached sublimation point yet. So no, the reverse is spontaneous. All right, so the loss of energy is a common feature of spontaneous change. So a lot of times you'll see a negative delta H. It'll be exothermic. Exothermic reactions tend to be spontaneous. However, endothermic reactions can be spontaneous too. And don't forget, you can tell if something's exothermic or endothermic by looking at delta H or by looking at its reaction profile. So here I can see reactants have more energy than products, so this would be exothermic. Here I can see reactants have less energy than products, so this would be endothermic. So this would have a negative delta H, whereas this would have positive delta H. And just don't forget, your activation energy is right here at the top. So reversible versus irreversible. A reversible process is when a system is changed in such a way that the system and the surroundings can be restored to their original state by exactly reversing the change. This is an ideal situation which does not exist. So think about ideal gases. Okay, they're not real, but we use them to make our calculations simple. Okay, so reversible processes, that's an ideal situation. So it does not exist, kind of like some of these things right here. All right, an irreversible process is one that cannot simply be reversed to restore the system and its surroundings to their original states. All processes that we see are irreversible. Okay, so in other words, something has to happen. Okay, it can't be perfectly, okay, let's just take away what we did, or let's just go back to the way we were. All right, so a process that occurs at a constant temperature is just called isothermal. Okay, so that means we're not allowing the temperature to change as the process is happening. So of course, if it's exothermic or endothermic, it's naturally wanting to absorb or release heat, so we would need it to be insulated or something like that. So, section 2, 19.2, entropy and second law of thermodynamics. Okay, so first law states, of course, energy is conserved. Second law is based on entropy. So entropy, we've talked about before, is represented by S, and it is the degree of randomness of distribution of energy of the molecules of a system. So it's the degree of disorder or randomness. So for isothermal processes, which we just talked about in the last section, that means the temperature doesn't change. Delta S, your change in entropy, is the Q of the reverse reaction over temperature. So notice it's not delta T because it's isothermal. Temperature is not changing. The units for entropy are usually joules per Kelvin, which that's going to become weird when we get to Gibbs free energy, because Gibbs free energy, delta G, is normally kilojoules, and delta H, or enthalpy change, is normally kilojoules. But then entropy is normally joules, so a lot of times you'll end up needing to convert it. All right, so let's look at our first sample exercise together. So it says the element mercury, Hg, is a silvery liquid at room temperature. The normal freezing point of mercury is negative 38.9 degrees Celsius, and its molar enthalpy of fusion is 2.29 kilojoules per mole. What is the entropy change of the system when 50 grams of mercury liquid freezes at the normal freezing point? Okay, so y'all, I know I'm going to be using this formula. Delta S is the negative Q of the reverse divided by T. In this case, remember, Q and delta H can be interchangeable as long as you're at constant pressure. So I can say negative delta H. All right, so let's look at this T. What's the problem with T? It's in Celsius. So I need to add 273 to this. And and this becomes 234.1 Kelvin. All right, so I can put that on bottom, 234.1 Kelvin. But now I got to deal with this delta H, okay? And it's not as easy as just trying to plug this number in, because of course this is kilojoules per mole. So they gave me how many grams, so you see where I'm headed. We're going to go from grams to moles. So I start with my 50 grams of mercury. And then of course 1 mole of mercury just equals molar mass, which in this case is 201 grams. And so that equals 0.25 moles of mercury. Okay, once I get that 0.25 moles of mercury, now I can use this delta H of fusion. But you have to keep in mind, fusion is melting. What are we doing? We are freezing. Okay, so that's where that negative comes into play, but it's already in the formula for us. All right, so we multiply by our 2.29 kilojoules per mole. Okay, and I end up getting 0.57 kilojoules. But remember, I told you that delta S is normally given in joules per Kelvin, so I changed that to 570 joules. Now technically this one didn't specify what unit it wanted entropy in, so if you kept it in kilojoules, that should still be fine. But what am I going to put right there? I'm going to put a negative. Okay, so it would be negative 570 joules per Kelvin. And so then I end up getting negative 2.43 joules per Kelvin. Just like that. Okay, so the important thing to remember is either A, you need to remember to switch the sign yourself, because this is for melting and you're doing freezing, and for opposite processes, delta H's sign changes. Or B, you can just remember that it has a negative in the formula. Either one works. Okay, so all we did for this one was we changed our grams to moles, utilized that molar heat of fusion, and then changed our temperature to Kelvin. So that one was pretty easy. All right, so now try the next one. I'll assume you've done that, we'll look at it together. So it says the normal boiling point of ethanol is 78.3 degrees Celsius, and its molar enthalpy of vaporization is 38.56 kilojoules per mole. What is the change in entropy of the system when 68.3 grams of our ethanol at 1 atm condenses to a liquid at the normal boiling point? Okay, so the thing to point out is vaporization is from liquid to gas. But what are we doing? We are condensing. Okay, so either A, you would need to make sure you remember to change the sign to negative, or B, you would use the formula. The thing is, I don't know that this formula is on your formula sheet for AP. So anyway, so it's negative Q of our reverse over our T. So again, I'm going to take my temperature and change it to Kelvin. So when I add 273, I got 351.3 Kelvin. All right. And so then the problem is, so this is kilojoules per mole. Okay, I just need joules. So I take my grams, 68.3 grams of my ethanol, and of course I change it to moles. So 1 mole is, in this case, my ethanol is 46 grams. So once I divide, I end up getting 1.48 moles of ethanol. And so then, of course, I have to use that delta H that they gave me. So I multiply it by my 38. And so again, you can either change it negative here, or you can change it negative when you plug it in. I've done it both ways before, so it really doesn't matter. So I ended up getting 57.07 kilojoules, or of course, because I'm going to go ahead and go to joules, I got 57,068.8 joules. Okay, obviously I went out more decimal places here. So anyway, all I did was just move that decimal over 3 spots. So 1, 2, 3. All right, so that's how many joules I got. So then I just plug into my formula. So I use negative of this, so negative 57,068.8 joules over, of course, my temperature, which is 351. Kelvin. And so once I solved, I ended up getting, because don't forget about that negative, I ended up getting negative 162.5 joules per Kelvin. So if this was a question on the AP exam, what I notice on the questions I look at is either A, they'll tell you what units they want. They'll say we want the change in entropy in joules per Kelvin. Or they won't tell you, but then they'll accept either kilojoules per Kelvin or joules per Kelvin. So you don't have to worry. If they don't tell you which one, they'll accept either. But a lot of times, like I said, I see that they just ask for a specific unit and clearly use that one. All right, so second law of thermodynamics still. The change in entropy for a spontaneous process is always positive. The second law of thermodynamics states that in any spontaneous, irreversible process, it results in an overall increase in entropy. So we want disorder, okay? We want more randomness, we want more disorder, and that's based on things like number of moles of gas, it's based on things like how many bonds can vibrate, it's based on things like temperature, how quickly the particles are moving, so we'll look at all of that stuff. All right, so section 19.3, the molecular interpretation of entropy. So now let's get into how do you know, is it increasing, decreasing, what's going on with that thing? So molecules can possess different types of motion. Translational motion is the movement of an entire particle from one place to another. So this is translational motion. The entire particle is moving around this area in the box. Then there's also vibrational motion, is where the atoms in a molecule stretch or shift the bonds. Okay, so see, here's examples of vibrational motion. And then rotational motion is when the entire molecule spins. So here you can see these molecules are spinning. Okay, so translational, the entire molecule moves from one place to another. Vibrational is kind of like a stretching and bending. And then rotational is just spinning, exactly what it sounds like. So, entropy is based on microstates. A microstate is a single possible arrangement of the positions and kinetic energies of the gas molecules when the gas is in a specific thermodynamic state. Entropy increases as the number of microstates increases. So in other words, y'all, the more options you have of how the particles are going to be arranged, the more entropy there is. Because the more options you have, the more disorder or randomness you have. So in most cases, oh, that should say and. Ooh, me and my typos. In most cases, an increase in entropy and the number of microstates can be caused by the following. An increase in temperature. Now, the faster the particles are moving, the more locations they can get to very quickly. An increase in volume. If something can spread out, it can be more random instead of being pushed together and orderly. An increase in the number of independently moving particles. That means gases. So the more gases you have. So really, the state of matter that has the least entropy is solid, because they're stuck in those fixed locations. Liquid would have a little bit more, because they can move past one another, but they're still not like spread out. And a gas out of the states of matter has a lot of entropy. So when a solution is formed by dissolving a solid into water, the solute particles gain entropy by separating from one another. So you go from an orderly solid, and once it gets to spread out and dissolve in the water, that's an increase in entropy. The water molecules have a decrease in entropy due to the attractions for the solute particles. So the water molecules were all random, but remember, we talked about this picture like 1 billion times. And y'all, I swear, if this is on the AP exam, y'all missed this. Some of y'all have missed this so many times. All right, so when you have the positive and you have the negative and you put the water molecules around it, the oxygen side of the water molecule attracts the positive, and then the hydrogen side of the water molecule attracts the negative. Why some of y'all have missed this so many times, I don't know. Remember, the AP questions are just so long and wordy, sometimes you can't figure out what it's asking. So because, see, now the water molecules, they're getting super orderly. They're surrounding those ions. They actually have a decrease in entropy. But the overall increase in entropy of splitting up all those perfectly ordered ions, that kind of overcomes it. All right, so again, we have super orderly sodium hydroxide, and we got some random water molecules happening. And then what happens is we've split up the ions, so the entropy of the sodium chloride has increased. But now those water molecules, they're all nice and orderly, so their entropy actually decreases some. So the attractions of the water molecules to the solute particles increases as the charge of the ions increase. So in other words, like a +1 charge is not going to attract a water molecule as much as a +2, or like a -2 would not attract as much as a -3. But we know that because of Coulomb's law. Attractions are based on charge and size, or radius. So the solution process normally has a net increase in entropy, because like I said, normally the entropy change of that ionic compound breaking apart outweighs the decrease in entropy when those water molecules get in those perfect attractions to the ions. So we can expect an increase in entropy for the following. 1, when gases are formed from liquids or solids. So anytime you have a phase change that goes to a gas, that's definitely an increase in entropy. Liquids or solutions are formed from solids. So remember, solids have the lowest entropy. The number of gas molecules increases during a chemical reaction. So, now that we know all this, let's do some exercises. So it says, predict whether the delta S is positive or negative for each of the following processes, assuming that each is at a constant temperature. Okay, so here we have a liquid going to a gas. So clearly that is an increase. Oh, look, I didn't realize all of them were going to come up. Well, never mind, I'll just write it out myself. So clearly that's an increase in entropy, so my delta S would be positive. Alright, here I have 2 aqueous, so they're floating around, but now they're becoming a solid. That's a very orderly. So my delta S here would be negative. I would have a decrease in entropy. Here I have 4 moles of solid and 3 moles of gas turning into 2 moles of solid. So I'm losing all the gas. So again, this one would also be a negative. There's going to be a decrease in entropy. And then finally, here I have 2 moles of gas to start with, and I'm ending with 2 moles of gas. So in this case, my delta S would be 0. Not going to be positive or negative. Okay, and so there we go. Positive, negative, negative, and 0. So y'all try the next one. Let me click. All right, y'all try this one. I'll assume you've done that. We'll look at it together. So we're indicating whether there's an increase or decrease. Okay, so here I have a solid to a gas, so that would be an increase in entropy. Here I have a solid and a gas coming together to make a solid. So I'm losing the gas, so that would be a decrease in entropy. All right, here I have 2 gases coming together to make a solid. That would be a decrease in entropy. Here I have 3 moles of gas coming together to make only 2 moles of gas. So that would also be a decrease. Okay, so hopefully so far you're finding these pretty easy. All right, now let's get to the trickier ones, okay, because they get a little trickier than just looking for who has the most moles of gas. All right, so let's look at our next ones. So these are a little bit trickier. All right, so I'll show you the first set and I'll let you try the second set. So it says, choose the sample of matter that has the greater entropy in each pair and explain your choice. All right, so we have 1 mole of solid sodium chloride or 1 mole of HCl gas at 25 degrees Celsius. This one's not tricky, it's easy. So who has more entropy? Obviously the HCl. Why? Because it's a gas. Okay. So next, we have 2 moles of HCl gas or 1 mole of HCl gas at 25 degrees. Well, again, this one's not very tricky either. Obviously, it's the 2 moles because there's more particles of gas. All right, here we have 1 mole of HCl gas or 1 mole of argon gas. Now, you're likely to say these are the same, but they're actually not. Okay, so remember about all that translational, rotational, vibrational energy we talked about? Argon is 1 atom. The only option it has is it can rotate and it can translate. It can't really do any vibrational because it has no bonds. HCl, on the other hand, can translate, it can rotate, but it can vibrate because that bond can stretch. So actually this one is HCl. So that's why I say it can get tricky sometimes, okay? Because there's more vibrational movement. All right, Ar is just 1 atom. It doesn't have the option to do this, whereas HCl does. Okay, so sometimes you gotta be super careful on these. All right, so y'all try these. I'll assume you've done them and we'll look at them together. So it says choose the substance with the greater entropy in each case. So you have 1 mole of H2 gas or 1 mole of I didn't finish, at STP, or 1 mole of H2 gas at 100 degrees Celsius and 0.5 atm. Okay, well STP, standard temperature, is 0 degrees Celsius. So what did we say about entropy? Entropy increases with temperature. So you should have gotten the 1 mole at the 100 degrees Celsius, because remember, particles are moving faster, so they have more microstates that they can get in. All right, part B, you have 1 mole of solid water at 0 or 1 mole of liquid water at 25. Well, here, I just need to compare states of matter. Liquid has more entropy than solid. All right, part C, you have 1 mole of H2 at STP or 1 mole of SO2 at STP. So again, we're both at the same temperature, standard temperature and pressure. There's 1 mole of each, so you need to think about who has more movement. H can translate, it can rotate, it can vibrate like this, because there's 2 H's. SO2 can translate, it can rotate, but look, it has 2 bonding areas, whereas H only has 1. Like H is going to look like this, whereas SO2 is going to look like this. Well, I mean, like you would have to draw your full Lewis-Dot structure and everything, but let's just, for simple terms, let's just put this. Okay, this is obviously not the correct Lewis-Dot structure. And so it has 2 areas where those bonds can do vibrations. So in other words, that would be the SO2. Okay, the more complex the molecule, the more bonding locations or domains it has, the more of those vibrational movements it can do. And then here we have 1 mole of N2O4 gas or 2 moles of NO2 gas. Well, here I don't even need to compare the molecule because I can compare the moles. The only time you have to focus on the molecule itself is if they're both gases, they're both at the same temperature, and you have the same amount. Any of those other things will trump whether it has more bonds or not. Okay, so in this case, I have 2 moles of NO2, so it's going to have the most entropy. All right, so hopefully you got those right. Y'all got a trickier set than I had on my sample. All right, so third and final law of thermodynamics. So the third law of thermodynamics states that the entropy of a pure crystalline substance at absolute 0 is 0. So entropy increases as a substance is heated. So of course a solid has the lowest, liquid is higher, and a gas has the highest entropy. And of course if you're comparing 2 gases, the gas with the higher temperature has a higher entropy, or like if you have different moles of gases, you know, we went over all of that. All right. So that is part 1. Hopefully so far you're finding this chapter pretty easy. Usually chapter 19 is not really that big of a struggle. The main thing I'll go ahead and tell you is you got to worry about signs. There's a lot of signs, positives and negatives, and so a lot of times you'll get those backwards. Okay, so just be aware for this whole chapter of signs.